Today we're going to derive the heat equation in a solid in 3 dimensions, so sort of a more general derivation than the last time when we only considered 1 dimension. So let's consider an arbitrary potato here. In continuum mechanics, we always like to draw potatoes as our arbitrary shape. So here's our shape. This is going to be a volume, so it's in 3 dimensions, even though I'm drawing it on a page that I'll label as V. And it's bounded by a surface that I'll label with S. Note my V, I like to draw a line through it. That's just a notation I picked up from an old professor. It's just helpful because it helps me distinguish between velocity, because my handwriting's not that neat. So we'll use capital V for volume. Inside our material, we're going to have a temperature, a function of x, y, z in time, and we're also going to have the heat flux vector. It will also be a function of x, y, z time. And our material is going to have constant properties of density, specific heat, and thermal conductivity. Now remember that the heat flux is a vector, so it has magnitude and direction, and its units are watts per square meter. And also on our volume, we have to also remember that we're going to need the normal vector. And so by default, we'll always define the normal vector to point outward everywhere along the surface. And remember, the normal vector is perpendicular to the surface, and it's defined everywhere. So the local normal vector. Now, just like in 1 dimension, we're going to need a conservation of energy statement. So it's the same as before. We're going to say the time rate of change of the energy stored inside our potato equals the net rate of heat in and out. Because now we have a kind of a closed surface, so we'll just talk about the net rate, whether the heat's coming in or out at a point, and we'll have to sum that up all around the surface. The units of this equation are simply energy comes in joules, and ddt has units of 1 over a second, so it's joules per second, which is equivalent to watts. All right, so now we're going to consider each of the terms in our equation one at a time. So let's start with the energy stored, or the thermal energy stored inside our potato. So this is going to be exactly what we had before when we did this in 1 dimension. So we're going to take an integral of the density times the heat capacity times the temperature, which is now a function of x, y, z in time, minus some reference. So that's sort of like, remember, energy we always have to define relative to some reference state. So he'll just call it Tref, a constant, integrated over dV, integrated over the entire volume. Whereas before, we just integrated this over a length x from like 0 to L. Now we're integrating over the whole potato. So when we write, this is a little bit of a shorthand, so I'm writing a single integral with respect to dV. What I really mean, or if we wanted to be more explicit, we could write 3 integrals. Right, this is rho c t, which is a function of x, y, z. So that might be a little more explicit way to write it, is to write out the 3 integrals integrating over x, y, z. However, we'll never use that notation. We'll always use the shorthand notation, single integral dV. And so all this means is when we take the integral over a volume, is we're just taking the energy of each little box here of temperature T, the very little box that's dx by dy by dz tall, and we're just basically summing them up. So this is no different than we did in 1 dimension, except now we're just integrating or averaging or summing up over the entire volume. So if we go to our equation, we had that the time rate of change of the energy stored so here I'm just going to write t, and I'm going to drop the notation x, y, z in time, where I'm writing out explicitly what's a function as, just for shorthand, but we have to remember rho and c are constants. Tref is a constant, but t is our function. It varies in space, x, y, and z, and time. I can split my integral into 2 pieces, one rho times c times the temperature, the other rho times c minus Tref. I got a little crowded here, but that's okay. I think you get the point that rho, c, and Tref are constants, so their time rate of change over the volume is 0, so I can drop that term. And also, since our volume of integration, our potato, is fixed in time, I can swap the order of integration and differentiation, and I can write this finally as the integral of rho c Now I'll use the partial derivative notation, the partial derivative of the temperature with respect to time integrated over the whole volume. And if you look back at our derivation in one dimension, you'll see this is precisely the same as we had in that case, except there we were only integrating one dimension. Here we're integrating over the entire volume. Now let's consider the net rate of heat going in and out of our potato. So here's my potato. The normal vector in being defined by just sort of agreement that it's always going outward. And at every point along the surface, there's also the heat flux vector. So it could have some angle relative to the normal. I'll just draw it that way here. And so what we want to know is what's the net rate of heat going out of the whole entire object. So let's just look at this point first. Remember, heat flux has units of watts per square meter. So it seems like if we can take the heat flux and integrate all the way around the surface, we would take care of the surface area, then we'd be left with watts, which would put us in the proper units. But we have to be a little bit careful, right? Because the heat flux vector has direction. If, for example, at this point it was pointing perpendicular to the surface, there'd be no heat flow leaving. If, on the other hand, it was aligned with the normal vector, then all the heat flux at that point would actually be leaving the domain. So what we have to do is be a little bit careful and say that the net rate that heat is leaving is going to be the heat flux vector at a point dotted with the normal vector, right? Because when we take the dot product, that gives the projection of this vector onto that one, just like so. And so q dot in is the component that's leaving the surface aligned with the normal vector. So by taking the dot product of the heat flux vector on the surface with the normal vector, that gives us the amount that's actually crossing that boundary, which is an important thing. Now all we have to do is take the amount that's leaving, and we need to sum it up. So we need to integrate over the entire surface ds. So here we mean we're going to go everywhere along the surface. We're going to calculate q dot in, and we're just going to sum up all those numbers all the way around the surface. So let's put this all together then. So we want to have the time rate of change of energy stored inside our potato equals the net rate of heat going in or out crossing the surface. So let's just substitute in the things we've already gotten. So we have the density times the heat capacity times the time derivative of the temperature field integrated over the whole potato. And then we have the heat flux vector dotted with the normal integrated around the surface. I put the minus sign here to get the sign correct, because if we have these two vectors aligned, it's a positive number, so heat's leaving the surface. Therefore, the energy inside should be decreasing. So now all I'm going to do is use some of our vector calculus results, and I'm going to use the divergence theorem, one of my favorite theorems. It simply relates a vector field dotted with the normal integrated around the surface to the divergence over the entire volume. We can group some stuff together. Now we're at a spot that was just like in the 1D problem, is that we have the integral of something, our something here being an equation, is equal to 0. And remember, we talked about when we have the integral of something equaling to 0, it can either be that this thing is equal to 0 everywhere, or there's some regions of positive and negative. However, here, remember, our dv is arbitrary, so our only choice, and our only choice, is that this thing is 0 everywhere. So therefore, we have a pointwise equation, which is our conservation of energy in a three-dimensional object. If you go back to our 1D example, you'll see we had the exact same result, except for here we just had the partial derivative of q with respect to x, because q, the heat flux vector, was only a 1D thing. It only depended on x, and it only pointed in the x direction. We can think a little bit physically about what this means. So remember, the divergence tells us whether all the arrows are kind of pointing or expanding from a point. So if we had a case where our heat flux vectors were all sort of pointing inwards, this would have, by definition, a negative divergence. So it'd have a negative sign. So that would mean if all these things are pointing, that the negative of the divergence would cancel with that negative, so it'd be positive, and the temperature would be increasing. We have energy accumulating at a point, so it's getting hotter. On the other hand, if our heat flux vectors were flowing out from a point, that would be positive, so that have a positive divergence, and therefore the positive divergence, we'd have the negative sign. So here the energy is all leaving a point, so it's cooling off. We can also have a situation where we have some of the vectors pointing in and some flowing out, and we end up with zero divergence. And in this case, the temperature would not be changing, it would just be sitting still. Okay, now as before, we have an equation, which is a single equation with two unknowns. We don't know the temperature field, we don't know the heat flux vector. So, just as before, we need a constitutive law that relates the heat flux vector to the temperature field. And we do this with our constitutive law being Fourier's law, which, remember, is not a fundamental law of nature, but it's just the way a lot of materials behave, and it's the same as before. We have the thermal conductivity K, but now we're going to find the vector as the gradient of the temperature. And remember, the gradient is just the derivative in our three directions, x, y, and z, denoted by their unit vectors I hat, j hat, and k hat. So if we just simply substitute this result into here, the negative signs will cancel, so I'll be left with a positive sign. If the thermal conductivity is constant, then we can simply pull it outside of these derivative operators, and we can write rho c time derivative of the temperature equals the thermal conductivity times the divergence of the gradient of the temperature, which is the same thing as the second derivative, or the Laplacian, of the temperature. So this is like a second derivative, spatial derivative. And again, as with 1D, since these are just constants that sit out front, we can lump them together. And remember, the product of the ratio of K over rho C was the thermal diffusivity, a material property we call alpha. And if we write that out in component form, the Laplacian, or the second derivative, is just the second spatial derivative in each direction summed up. So the second derivative in x, y, and z all summed